Hey guys, my name is Alan Yoon, and this is lab report number 3. The goal of this lab is to find the mass of a black hole. The problem, however, is that we are only given the position data for a star's motion along with mass and relative locations. However, we really need only apply the physics that we have already learned. Combining knowledge of Newton's second law, or the momentum principle, the mechanics of circular motion, and Newton's law of universal gravitation, we can create a computational model that not only tracks the star's orbital motion, but can also estimate the black hole's mass based on the forces in play. The result? Based on the given position data of the star, the mass of the star being 1.9890 times 10 to the 30 kilograms, and the center of the black hole located at this given position, the mass of the black hole was found to be approximately 2.9848 times 10 to the 31 kilograms, and this was deemed accurate as per WebAssign. For our fundamental principles, we are first going to talk about Newton's second law, or the momentum principle, which is given by this common form where the final momentum equals the initial momentum plus F net times delta t. This lab utilizes a given CSV file of the position data of the star across several hundred time intervals. Using those positions, we can calculate the velocity of the star between each two positions. And using those velocities, we can calculate the change in velocity, or the change in momentum, which is how we find the net force, as shown by the illustration from our lecture videos. And reiterating all of these values gives us the ever-changing net force that we want to visualize. Now let's look at our code. This first part of our code reads in the position data from the given CSV file in this while loop and calculates the velocity between each step with the method illustrated before, and the velocities are stored inside this running list. The second part of our code takes the velocities that were found and calculates a change in velocity along with a change in momentum. Using this change in momentum, we can find dp dt, or the net force that we want. The next fundamental principle is circular motion, which is simply an application of the momentum principle. Using the net force of the system, we can break the force down into multiple components. The parallel component that determines the rate of change of speed of the system, and the perpendicular component that affects the rate of change of direction. This is equated with the form using change in momentum. By taking the derivative of this basic momentum form, which is magnitude times direction, we see the product rule that we all learned from basic calculus take place. The left component represents the F net parallel by showing the change in momentum in the direction of motion, and the right component represents F net perpendicular by showing the change in direction during the given momentum. If we look at our code, we can see each component broken down. F net is found using dp dt, F net parallel is found using dp dt parallel, which is solved for using each of the components discussed earlier, which was the direction of motion and the rate of change of momentum. And instead of directly solving for the perpendicular component, we subtract the parallel component from the net force to obtain that value. With that bit of algebra, we eventually obtain F net parallel, and F net perpendicular, all of which are displayed by arrows in the model. This is a good moment to talk about our what does it mean question. So while mathematically the values of F net and dp dt are equivalent as per Newton's second law, their roles and applications to physics systems are slightly different. As this image from our lecture video explains, changes in momentum can be observed and measured. F net is a quality of the system that cannot be directly measured, but we can see the effects of that force in the form of change in momentum. Momentum is the effect of the F net. Momentum is a quantity, while F net is a quality. And the same difference applies to the perpendicular and parallel components of each. The next fundamental principle is gravity. Using the calculated net force, all of which is deemed to come from gravitational interactions, we can apply Newton's law of universal gravitation. By simply rearranging the components of this equation, we can apply this to our code to solve for the mass of the black hole. We can see each component in the code: the magnitude of the net force, the distance, the mass of the star, and the gravitational constant g. Now let's go directly to our code. Simply scrolling, we see the initial parameters of location and mass, we see the time step delta t, we see all of the components of the code that were previously mentioned in detail, and finally we see the arrows that will illustrate the components of our net force. If we run this code, this is what our model looks like. As the distance is shorter, the arrows grow larger, indicating greater force. As we note, the motion data only tracks about 1/2 of an entire revolution. And in our outputs, we see the calculated mass of the black hole, which is what was shown at the beginning of this report, 2.9848 times 10 to the 31 kilograms. Now for our what if question. If the motion data of the star were exactly the same, there cannot possibly be a difference to be determined for the new black hole's mass. The motion data is the only tangible evidence we have of the force acting on the star. If the motion is the same, the velocities are the same, and the momentum is the same, so the forces acting on the star must be the same. And since the only force acting on the star is the gravitational force, the mass of the new black hole must be concluded to be the same. However, if the motion data displayed some variations, then we can notice a change in the system, and in this case, the mass of the new black hole must be different. That is it for this lab. In conclusion, we see that we can estimate the mass of a black hole simply with the motion data of a star and a little physics. Thank you.